Hello everyone, welcome to my channel. In this series, I'm going to explain the exercise of Andrew Karpathy's video. For those unfamiliar about Andrew Karpathy, he is a PhD of Stanford University and have a solid working experience in Tesla and OpenAI. He has posted a lot of video to explain how to build AI in his own YouTube channel. I found out his video is very well structured and teach you how to build the AI from scratch. So let's dive in. In this video, I'm going to go through the exercise from this video. Let's build GPT from scratch in code spelled out, which was posted in 2023. In that video, he built the transformer decoder, which is backbone of GPT-2 and GPT-3. And he literally built every single element of transformer decoder in code. So if you haven't checked it yet, I highly recommend to check it out first and trying to solve the exercise by yourself. But if you get stuck, don't worry, that's why I'm making this video. In the following series, I'm going to explain the exercise one by one, but in this video, I just talk about the exercise 1. Let's dive in. The title here is the n-dimensional tensor mastery challenge. The goal here is to combine the head and multi-head attention into one classes that process all the head in parallel. Hint here is just treat the head as another batch dimension. In Andrew Karpathy's original video, he builds the attention mechanism exactly like the formula in the paper, attention is all you need. He separated the queries, the keys, the values to make it very understandable. However, in real-world organism, we don't just care about the readability. We also care about the parallel computation. The original code, I will show you later, wasn't optimized for this. So we are going to improve it. We want the code to be functionally equivalent, but much more efficient by calculating everything in parallel. So let's examine the code first. We have a head and multi-head attention class. In the head class, he initialized the weight matrix. Here he initialized the WK and also WQ and WB. And in the forward pass, the K is just calculated simply by multiplying the input tensor by this weight matrix. And it's also same for the Q and V. And also the weight matrix is calculated by softmax applied to Q multiplying by the transposer of K and divided by the square root of the D. And this value needs to multiply by the value matrix. So we just got the result of the single independent head. And in the multi-head attention, he just stacks all the independent heads together and to pass through a projection layer. Here is projection layer. He passed through the projection layer and use dropouts to avoid the overfitting. So it's very simple and standard multi-head attention mechanism. But the problem here is we can see for each head we initialize the 3 different weight matrices, and imagine we have n different heads. So we need to initialize 3n different metrics, which is very inefficient by calculating. So can we just initialize one giant matrix that's combine all the different 3n metrics together? The answer is yes, we can do it. Let's recall the matrix multiplication first. Imagine we have a matrix A multiplied by B is equal to C. We have matrix A, matrix B, and matrix C. We can examine the first columns of the matrix C. The first elements of the first column of C is calculate it by the first row of A matrix, multiply the first columns of B matrix. The second element is calculated by the second row of A and the first columns of B. And the third is third row of A and first row of B. So we can see the first columns of C is only relevant to the first column of B as a whole A matrix. We can write a formula out. A multiplied by the jth columns of B matrix is equal to the jth columns of C matrix. That gives us a hint. Maybe we can just initialize a very, very large matrix of B and doing it in forward pass and then cutting the result matrix in the small pieces. What's that mean? Because we have QKV is calculated by the input tensor multiplying by the weight matrix, right? So we can see, like here, input tensor is the same thing. So maybe we can just stack vertically the weight matrix together. Then we can only just initialize it in one time and cut the result matrix in the small QKV. So we have an input tensor here, and also we have the big giant matrix. The first is the weight matrix of Q. The second is the weight matrix of K. And the third is the weight matrix of B. The result, like I talked before, the first two is only relevant to the WQ. So the second part is only relevant to the WK. And the third part is only relevant to the WV. So we can actually initialize only one big matrix and then cut it in the small pieces. So let's take a look at the answer. In the new multi-head attention classes, we only initialize one giant matrix with dimensions d by 3d. How do we come up with a 3d? It's actually calculated by 3 is each head we need to initialize 3 different weight matrix, and each matrix weight matrix is with the dimension d divided by n. This is the head size. And actually totally we have n different heads, so we end up with a 3D. By the forward pass, firstly we need to calculate the input tensor multiplied by the big QKV matrix we just initialized. We end up with the big matrix with the dimension b by t by 3d. B is the batch dimension, t is the sequence length, and 3d is just the combined channel dimensions. Firstly, we need to split it into the QKV, big Q, big K, big V matrix, and each of matrix is with B by T by D dimensions. And what's the next step? We need to split each Q, each K, each V into the small pieces, into the n different heads. So we end up with the B by N by T by D divided by N, which is the head size matrix. And after that, we can doing the same logic we talked before by the head class. We just calculate first the attention weight matrix and multiply it by the value matrix, which is just the same. So we end up with the result is B by N by T by head size. We can just take see this matrix as the output of the each head, but stacked it each other on the second dimensions. So the last step we need to do is just stretch it to stack the different output of the different heads into one dimensions. It's just use build functions to transfer it to dimension b by t by d, and then pass it through the projection layer. It doesn't change the dimensions, so we still got a d by t by d dimensions, and that is output of our multi-head attention layer. In this multi-head attention layers, we just parallelly calculated each different head together. We just only initialize only one big giant matrix instead of initialize 3n matrix separately. So let's take a look at the result. I use the same structure for first GPT transformer decoder. We just use our new parallel multi-head attention layer. For 2000 steps, it takes 147 seconds, and for the old structure, we only use the old multi-head attention, head classes and multi-head attention. It takes 187 seconds. That means with our new multi-head attention layer, we saved almost 40 seconds in 2000 steps. So it's a huge forward actually. It's a huge steps. So that's my first video to talking about the exercise 1. If you like it, hit the like button and just leave the comment below. I will put all the links in the description box, and yeah, we will see you in the next video.